Welcome back. In this video, we're going to be taking a look at wave motion. Now, wave motion is actually kind of built on simple harmonic oscillators, but there's an important difference. Harmonic oscillators are a function of a single variable time, whereas waves are a function of both space and time. So for example, if we have a transverse wave, we're interested in a transverse wave, meaning that, let's say it's like a wave on a string, for example. We're interested in finding out the height at any point in a string where you can look at any point in a string in x at any given time. And typically, to investigate these types of problems, we'll treat one of these variables only. So for example, we may be interested in finding what's happening at 3 seconds everywhere on the string at all x. In other words, if the string looks like this at 3 seconds, then at this x, y may be big, but at this x, y may be negative. At this x, y may be 0. These types of graphs are called snapshot graphs because we're looking at a snapshot of the wave at a particular instance in time. On the other hand, we may be interested in what's happening at a particular point for different times. So for example, if the wave is on a long string, I may be interested in what's happening at the point 2 centimeters, but I want to know what's happening at that point in all the history of time. And for this reason, this is called a history graph. So these may have different, they may be pertinent to different situations, and we'll find that for the problem we're going to be looking at, one of these may be a little more relevant. With that being said, why don't you go ahead and take a look at the problem statement. Now in this problem, we have a few different things going on. We have speeds given to us, one of which is the wave speed, and it's moving in the positive x direction. We also have some information about what's happening at time t equals 0 at a particular part of the string. And we also have some information about that same part of the string, but about its transverse speed. And we're asked to find these quantities down here. So let's start with the first one. We're trying to find the frequency of this wave. Now, the frequency of the wave, normally you would just use maybe the following expression, something like this, that the velocity equals the wavelength times the frequency. Because we do have the velocity of the wave is 80 meters per second, and we're looking for frequency, but the problem is we don't have the wavelength given to us explicitly. Actually, let's use a different method. We're going to use some of this information about the transverse motion. Now, keep in mind that this transverse motion refers to, let me just go ahead and just maybe let me go ahead and draw a snapshot graph. So a snapshot graph is the graph of what the situation looks like on the entire string at t equals 0. We don't know what's happening everywhere. All we know is that at t equals 0, the very x equals 0 part of the string is going to have a displacement of 4 centimeters. So I can actually go ahead and draw that first. And let me go ahead and just draw the axes. So whenever you draw a snapshot graph, it's best to be very explicit about what you're taking a snapshot of. And in this case, the snapshot occurs at t equals 0. So just kind of draw that in the corner, write that in the corner somewhere. And the axes are x and y. History graphs have an axis of time in y. What are we given? We're given the fact that at the x equals 0 portion, its displacement is 4 centimeters. Okay, so that's 4 centimeters up there. And we know that it's momentarily stationary. We don't really know anything else about the graph. So the wave, we don't know if this wave is maybe that's part of the wave that's going up and going to go back down, or if it's actually the crest of the wave or something different. We don't really know where it is at this point. What we're trying to find here is a frequency. Now, if we think about this part of the wave, so every single portion of this wave, no matter how it's drawn, and actually let me go ahead and I'll go ahead and just draw it in. No, I won't do that yet, but let's just say there's any part of the wave, this thing is going to be moving up and down. So every single part of the wave actually is its own harmonic oscillator. It's going to be oscillating up and down, and the time it takes to go back to its original position is 1 period, and the frequency at which this occurs is the frequency of the wave itself. So if I looked at any portion of this wave, it would do the same thing. It would move up and down with a frequency that equals the frequency of the wave motion. So what we can do is actually look at the transverse motion because we have some information about transverse speeds. So what we want to do is maybe find an expression for the transverse velocity, and then we can set that maybe equal to 16, kind of go from there. Let's start out with an expression for just the wave in general. And it's okay that we don't know these quantities yet. We do have some information about what's happening at 0, 0, so maybe we can plug that in. Now, when we're talking about transverse motion, that just means how is the y value changing? In other words, at this point at x equals 0, its distance is 4 centimeters, but I want to find out what its velocity is. In other words, how is y changing? dy dt. So if I just take a simple derivative of this expression, I think you get some minus signs that cancel, and you have an omega that comes out to the front. Now what do we know? We know that the max transverse speed at this point is 16 meters per second. We also know that the general expression for the transverse speed is given by this formula. Well, the speed, of course, depends on where you are, here x equals 0, and the time. So it's changing all the time. But its maximum is going to be given by whatever the maximum of this entire quantity is. The max of this portion is just 1 because it's a sine function. So the max of this whole thing is just going to be a times omega. We know that the max equals 16, so why don't we go ahead and set that equal? Again, this is the transverse speed, which depends on time and position, but its max is going to be the coefficient because the max of sine is just 1. So we're kind of making some progress here. What are we trying to look for? We're looking for the frequency. This has the frequency that we need. All right, so the take-home message here is that we can use transverse motion to find frequencies if we also know the amplitude. Do we know the amplitude? Here, in this case, we do. And it's because we know that at x equals 0, t equals 0, it's displaced by 4 centimeters from the x-axis, and it's also stationary. Again, using the fact that this is a harmonic oscillator, it's oscillating up and down, and like all harmonic oscillators, it always reaches its max extension, in other words, its amplitude, when it's stationary. So here it's going to be moving at a very quick speed, slowing down until it gets here, stops, and then turns around. So its amplitude is this much, and it's going to oscillate between plus 4 centimeters and minus 4 centimeters. Right, so the amplitude is 4 centimeters because it's stationary. So plugging that in, we find that the angular frequency is 16 over 0.4, which is 400 radians per second. And then you can use that to easily get the frequency in hertz, which is just that guy divided by 2 pi by definition. And that'll give you 64 hertz. All right, so that's the answer to the first part of the question. Now the second part of the question asks us to find the first time x equals 0 at which it hits its max transverse speed. So the point at x equals 0, so we're still talking about this part of the string. When will it hit its max transverse speed? Actually, before I go on, let me finish drawing in this wave here. Now we know this guy is at its amplitude because it's stationary. So this is the highest point the wave can reach. So this is actually a crest of the wave. So in this snapshot at t equals 0, this is indeed a crest, and I can actually draw this all the way in. So that's what the wave looks like at t equals 0. All these parts are moving up and down as harmonic oscillators. And the next part's asking us, what is the transverse speed of this portion of the wave? How long does it take for this guy to reach its max transverse speed? Well, right now at t equals 0, its transverse speed is 0 because it's stationary. It's going to speed up very quickly, and then at this point, like all harmonic oscillators, it'll reach its max speed when it's at equilibrium. So it maxes out at speed here and then slows down until it gets to minus 4, and then reverses direction. So what we need to do is find out how long it takes to get to the y equals 0 part of this graph here. That's actually not too hard because we know that it'll take one period to go all the way back. So it takes one period to go back where it started, and it takes equal amounts to go in each one of these. So this is going to be a quarter period, quarter period, quarter period, and then quarter period. In other words, the time it takes to get from here to here is a period divided by 4. Right? So for the second part of the question, it says first time for the position at x equals 0 to hit its max speed. That's just going to be the period divided by 4. And the reason that's useful is because we have the frequency, and the period is just 1 over the frequency. So this is just going to be 1 over the frequency times 1/4, which is, given a frequency of 64 hertz, plugging that in should give you about 0.0039, and the units is seconds. Okay, so that's the second part of the question. So that's how long it takes for this guy to go from here to here. At that point, it'll max out its speed, and then it'll take another 0.0039 seconds to get to the bottom where it'll stop again and turn around. Now, the last part of the question asks us to find an expression for the general expression for the wave. So we'll start from what we know, which is a cosine kx minus omega t. We know it's minus because this is moving to the right, so I'm going to keep it as a minus. Now we got to see what we're missing here. The amplitude we know. Amplitude is 0.04. K we don't know. Omega we do know. It's 400. And then phi we also don't know. So we need to find expressions for these missing quantities. For k, here's where we can use the actual wave speed. Remember, wave speed is, if you use this formula and rewrite it, I'll rewrite lambda as 2 pi over k. That's how k is defined in the first place. So this just equals 2 pi over k. And then the frequency is, by definition, it is omega over 2 pi. So another way you can write velocity is by just writing omega over k, which tells us that if we're looking for k, we can just divide the velocity into the omega, which we have both those quantities, 480. So that just equals 5. And that's given in radians per meter. All right, so the only thing we need now is the phi. And the best way to do this actually is to go ahead and plug in, if we know any initial conditions at all, any given point of the string, then we can plug that in to find the last quantity. We do know that at x equals 0, t equals 0, the string is at a displacement of 4 centimeters and it's stationary. So we know y at x equals 0, t equals 0. If we plug that in, and for the last part, let me write that here. So use y of 0, 0 is 0.04. All right. So plugging that in here, we're going to get 0.04 equals, amplitude again is also 0.04, times the cosine of 0, 0. We're going to plug in 0 for x, 0 for t. Those guys go away. All you have is cosine of phi. So you just get that the cosine of phi equals 1, which tells us that phi equals 0. All right. So this can be very naturally described by the cosine function because the phase goes away. The final expression for the wave is oops, 0.04, sorry. 0.04 times cosine. K is 5, and omega is 400, and then phi is 0. So the final expression for the wave is this guy right here. Had we had this at the very beginning, we could find a lot of these quantities by plugging in values, by looking at what k is, omega is. So we really kind of work this backwards by using our knowledge of the physical system and the fact that this transverse motion has a lot of quantities hidden inside of it. So we use the transverse displacement, transverse velocities, and from there we're able to find things like frequencies, periods, and then finally we found the wave expression. So that's all the problem is asking. I'm going to ask one more question to you guys, which is not in the problem statement, and that's the following. I want you guys to draw 2 graphs. The first graph is a history graph of the position of x equals 0. Again, so it's basically saying I want a graph of y versus t of this position, of this point right here. So to start you off, it'll obviously start at y equals 4 because it's at t equals 0, it's at y equals 4. But then you want to find out how it changes over time. And then do the same thing for the velocity graph. So I want a history graph of the position and the velocity of x equals 0. So you should have 2 graphs whose x-axis, whose this axis is t, and this axis is y. And one should be for displacement, and one should be for the transverse velocity, both for the x equals 0 portion of this wave. Give that a go, and we'll come back and just finish up the problem. I've drawn the axes up here for these 2 history graphs, but notice that first of all, I've labeled which part of the string I'm looking for. Being a history graph, you can label it with x equals something, depending what part of the string is in question. And then the axes are y and t, and then for the transverse velocity, it's dy, dt, and t. Now, there's a couple ways to go about this. So let me first just do it mathematically, and then we'll think about the intuition. Mathematically, we have an expression for y. What we're looking for is y as a function of time only for x equals 0. So I can just plug in x equals 0 here. And that gives me this expression. And if you recall back to some trigonometric identities, a cosine of a negative quantity is the same thing as a cosine of the positive quantity. So this just is a cosine graph. And it's a positive cosine graph. So really what we're looking for is like the positives and negatives here. So this is a positive cosine graph, and it should just look like this. Does that make sense? We know that at the beginning of the beginning of the clock where t equals 0, the y equals at 4 centimeters and it's stationary. So we knew it was at 4 centimeters to start off with. And we also remember that it's on the, when we had the snapshot graph, it was moving up and down. So it started at 4 centimeters and was moving towards the x-axis. Y was decreasing. And you can see that here, y is decreasing as time goes on. At some point, you're going to hit the x-axis, and then you're going to go to negative. So once it hits the x-axis, it's going to go back down to negative and come back up. So this graph actually makes sense with the physical scenario. In addition, we can actually label the initial point up here, which is 4 centimeters. It starts at 4 centimeters, goes down to negative 4 centimeters. Now for the transverse velocity, we'll do the same thing, except we'll take the derivative first. So the derivative will give you dy dt. With respect to time, we'll bring out the 400 and there's a minus sign in front. And there's also a minus sign from the cosine derivative, so that should give you an overall positive. And you don't need to worry about the values, really, just about the general signs. And then if we're only looking at the point where x equals 0, then we can just go ahead and plug in 0 for x here. And the negative, the sign of a negative is actually going to give you a negative sign. So the sign is the one where you take the negative inside the parentheses. It'll bring the sign out front as a negative. So I'll put the negative here. And that's the same thing as the sine of 400t. So in this case, we're going to have a negative sign graph. So this velocity actually looks like this. Remember, signs start at 0. But the normal sign looks like this. The negative sign goes down and back up. Now, does that make sense? That does make sense because if we have a position starting at 4 centimeters and then moving towards the x-axis, its initial velocity is negative, which is what we're getting here. As time goes on, the initial velocity is negative. And then at some point, its velocity reaches a maximum value of 16 meters per second. And then turns back around, becomes 0, and then starts going in the positive direction. So this makes sense with the physical intuition based on what we were told in the problem. Let me stop there with this problem. It was a few different steps, and it was a little lengthy, so go back and just take a look at the reasoning and the mathematics, and then take a look at the summary if you need to. We'll see you next time.